One final thing for today is R. We only slightly touched on R so far. I didn't show you the important thing. The important thing, which is on the slide, and as usual, I will jump the slide and show you directly in R instead. I go up again and use my toy example from the beginning of my lecture, right? This was the example with an average of 5 and those 3 mean averages. You can plot it. Actually, an important thing is actually this one here, the treatment. Look at this. For doing analysis of variance, we need the information of group membership. Now I have the complete column of data. I have the Y, that's just a list of 12 data points, right? So to be able to do analysis of variance, I need the information about which groups do they come from. I do that by defining a treatment factor. A treatment factor is basically a list of the numbers 1, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3. Then there is something in R that I can actually inform R that I'm going to use this as a factor, meaning I'm going to use it as a categorical grouping information rather than using the numbers 1, 2, and 3. This means that I could have used any codes for these groups. I could have wrote 5, 7, and 9. I could have wrote A, B, and C. It can handle that also, actually. I could have used any names, just that they are different between the 3 and same within. So you can see if I have this treatment factor, you can see the way that R is giving me the information, that it tells me a bit differently than if it was quantitative. I have 3 levels and they come as 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3. Having done that, actually there are some nice generic features in R that such treatment factors you can use in many different ways in your R handling. For instance, if you plot this, you don't even have to tell. If you plot it with the factor comma y, it automatically produces the box plot by group because it knows that it's. So there are a lot of generic built-in sort of inheritance and in R that you can try and then see if it makes sense and if people did it. Here's the important new thing for you. We can use the same inbuilt function called LM, standing for linear model, to produce the analysis of variance. Like this, where we have that the Y is a function of the treatment. Last week we had Y was a function of X, right? Today, Y is a function of the grouping. We have 3 different group levels. That's how we should see it. And then we can apply the inbuilt Anova function also. That's also a function in R that actually produces the Anova table for us. And here's the output, as you should become familiar with. And it's not difficult because it's just the same output I've been discussed now, that the output from R is that you have, maybe in a different order, but you have the degrees of freedom, you have the sum of squares, SS, you have the mean square, that's the MS, you have the F, and it also finds the p-value too. It even tells you the story about the p-value, that the p-value is very small. If you would be in doubt of that by looking at the number, it informs you about that also. Was there a difference in my toy example? I didn't complete the computation of my toy example, but here I do. Yes, the 3 groups of my toy example were extremely different, or extremely certainly different. Whether you will call the size of the difference extreme, that's a matter of subject matter interpretation. The statistical difference is pretty clear on my toy example, right? Here is just to show you, what if I only used 2 of the groups? Look. That is group 1 and 2. I could also use Anova on that one. I could also use a t-test on that one. And look at this. The p-value for the t-test, 0.0001683. the p-value for the f-test in the Anova, 0.0001683, exactly the same thing. That's what I told you previously. So for two groups, be my guest, use the f from the Anova, or use the t from back then, I don't care. Right? It's the same thing, so you can do whatever you want. And also here, we should focus on the end of this. Here's an example of, I'll share this with you as I usually do, of course, the updated one. Here's a way of reading in some data from a data table, and the data comes like this. This is the gold, platinum, glass example that comes like this, and you could do the Anova on this one, and we get the result that I already shared with you from the example. We need to do the two-way thing here, right? I have example, treatment, and block. Let's just look at the data. This is some simple data from the book. Now look at what I did here. I used sort of the way in R. I mean, this is a bit R technical. You may not want to go into this, but it's quite convenient if you want. I created a data frame. That's the way of collecting data sets in R, either by reading in material or creating them yourself, by having first a column of data, then I had the treatment column, and then I have the block column. So this is a toy example, a book example of the blocked. It's not the hearing aid example. Then, actually a bit tedious, but you have to do the factor thing. You have to tell R that that's a classical mistake when you do it in R, that you forget to tell R to treat it as a factor, because if you don't tell R that, R is doing a linear regression on the numbers like I taught you last time. And that's not what I want R to do now. I want it to do the analysis of variance. And then we can do, and here's the new thing, the way to do the two-way Anova is using the same function, lm to y, but now it's not only a function of treatment, it's a function of treatment plus block. Treatment and block are the names of my two columns, coding for whether an observation belongs to one treatment or the other, or one block or the other. So there are two columns of coding here. And we can do the Anova for this one. And as you can see, the output is the following. Again, I remind you, this is a toy example. This is not the hearing aid example. We get the degrees of freedom. We get the sums of squares. We get the mean square. We get both of the f's, and we get both of the p-values. As an absolutely final thing, let me dwell again. I'll show you how explicitly we can see this thing about it being a good idea to do blocked experiment. Since what happens if we take a blocked data set and wrongly, because we could forget about the blocks and just think about it as different groups and forget about the other way of the table, right? That would be a wrong way of doing it, but that could be a classical mistake. What happens then? What happens? So it's the same data here. Look at this. Here was the upper thing was the correct two-way analysis. The lower thing was the wrong one-way analysis, right? The treatment, not the p-value, but the treatment sums of squares and means of squares, no change. That's what I told you. That's the same computation. But now look at the difference. Instead of having block and residuals with 3 and 6 degrees of freedom, I have residuals with 9 degrees of freedom. That's the sum of those two, right? Instead of having a sum of square of 90 and 52, 90 for block, 52 for residual or errors, I have a joint residual down in the wrong one-way. They have been put together if I do a one-way analysis. The 90 and 52 have been added together to 142. So this explicitly shows, you could see it the other way around, that if you go from the one-way to the two-way, I have extracted most of the residual error from the one-way approach has been put into the block thing and leaves me a much smaller value than here, a factor 2, and produces in the two-way analysis a larger F than in the one-way, right? So that's the benefit of it, and that's how it's linked together. And that's it for today, ladies and gentlemen. This was the final part of the course, so we're all done. I have a nice summary lecture next time, so if you want to join in, go there, right?